ماشي يا عبد الله صحتين. سبقتك أنا بالقهوة. Okay. There are no questions. Let's continue. Last time we left with the last topic, small topic actually from chapter 3, which was where we revisited other types of gates. We talked again about the XOR, we talked about the XNOR, and we also introduced a new gate, which was the if you remember, the tri-state buffer. And we said this is very important gate. Logically, this gate is represented using this symbol, which and it has 2 inputs and 1 output. If we call, let's say, this is X and this is Y, we said this input is called the enable or the control input, which controls the operation of this gate. And this is the operation of this gate is very simple. If E equals 0, this implies that the gate is disabled. 0, using this configuration implied the gate is disabled, which implies that Y is what? What will be Y? We said Y, when E is equals 0, this disables X from reaching to Y. In other words, Y or the output is not connected to X, so Y cannot take the value of X. Y is not affected by X. So we said we can't, since there is no path between X and Y, there is no connection, then the voltage at this point is not defined or is unknown. To be more precise, is not known, which implies there is a very high resistance between X and Y, and we called it zeta. And I cannot write equals because zeta is not a value, it is a state. It's not a value, it's not logic 0 or logic 1, but there is a very high resistance here that prevents X from going or passing through to Y. Now, when E is 1, we said that simply Y is equal to X. Y is equal to X. So it's better here to say that Y is not known or undefined. But when we draw the truth table last time, we put zeta to indicate that there is no connection between X and Y. And we said that this gate is very important when it comes to interfacing or connecting multiple systems. And we showed an example. If we have 2 systems, A and B, and we want, and these 2 systems are supposed to send data to C, instead of having 2 separate wires or channels for these 2 systems, we simply can have 1 wire, and then we let these 2 systems share this wire using a tri-state buffer. But one of these systems is allowed to use the shared wire at any instant of time. And of course, this means if we want to use the wire, we have to enable its tri-state buffer, and we have to disable the tri-state buffer connected to B, and the opposite is true. So usually if we have 2 systems like this, we need 2 control signals, or simply here in this case, only one of these has to be 1. So we can say this is E, and we put here an inverter like this. So this means that the control signal for this tri-state buffer is the opposite of this one. So one of these will be enabled at any instant of time. And we will get back to this later in chapter 4. This is very important circuit. Despite its simplicity, it has a name. Now, if we have more than 2, then we need some kind of circuit here that we will introduce in chapter 4. But this is basically what we talked about last time. Okay, so let's just take one or two examples on this. For example, let's say we have this circuit. Let's say we have here X, we have here 1, and we have here Y bar, let's say, and we have here X. And here we have F of X, Y. So this is a circuit that is supposed to implement F of X, Y. It is a circuit that's supposed to implement F of X, Y. So now the question, what is F of X, Y, let's say, as a sum of minterms? As a sum of minterms. So this is basically, I am giving you the circuit and you are required to tell me what are the minterms. And this is called analysis. You want to analyze this circuit in order to determine the expression of the logic function in some form. In this case, we are requiring or asking for the sum of minterms. So how to do that? Basically, you can do this straightforward. You need to probe this circuit. You need to test this circuit by inputting different values for X and Y. So if we put the truth table, for example, 0, 0, 0, 1, 1, 0, 1, 1, in order to know F, given the circuit, we don't have the function expression. Given the function, we need, in this case, to try all possible combinations. So if we take the first combination, which is 0, 0, X is 0, Y is 0, what will be F? So if X is 0, this is disabled. If X is 0 here, this will be 1. So this tri-state buffer is enabled. This tri-state buffer is disabled. So we don't care about what's going on here because there is no path from the data input of the tri-state buffer to the output. So what is connected to the output is basically the input of the bottom tri-state buffer, which is, if this is 1, what will pass through here? Y bar, and Y is originally 0. So what will pass through here? 0 bar, which is 1. Because the input is Y bar, and Y is 0. So here is 1. So 1 will go, and F will be 1. The same thing we will have when X is also 0 and Y is 1, because X is 0 implies this tri-state buffer is enabled, this tri-state buffer is disabled, and the difference here is in the data. Y is 1, so Y bar 1 becomes 0, so this will become 0 and F will be 0. So this is, if you can imagine it, if X is 0, you enable this buffer and you disable this buffer. So whatever is available here will pass through to F, and this one is disconnected. Now the opposite happens in the rest of the combinations. When X is 1, this tri-state buffer is enabled, and this tri-state buffer is disabled. So we don't care about this buffer. We need to care or to look after the top buffer. So now when X is 1, 1 passes through to F. So what will be the function when the input is 1, 0? It will be 1. And again, when X is 1 and Y is 1, the function also will be 1. So basically, F is sum of minterms 0, 2, and 3. 0, 2, and 3. So I just, based on my understanding of the operation of the tri-state buffer, I just substituted different values. Okay. Another way to do it, for example, if somebody asks you what is the logic expression of f of xy in general, you can say when x is 1, here. You take each tri-state buffer one at a time. When X is 1, 1 passes. So X is 1. When X is 1, 1 passes through. So it is X and 1. Or when X is 0, in other words, X bar, and what passes through? Y bar. So this is X or X bar, Y bar. But this is as a sum of product, of course. And how did I get this expression? Simply, I said, when X is 1, 1 passes through. So it is something like AND gate. X and 1 will be F. Or when the X is 0, Y bar passes through. So it is X bar and Y bar. So this is the condition imposed by the first tri-state buffer. And this is the condition imposed by the second tri-state buffer. So you can do it like this, which is a sum of minterms in this case. Or you can read it directly as a sum of product. You say F is simply X and this, or it is simply X bar, here we have X bar and Y bar. And if somebody asks you, for example, this is something on the side, to simplify this function, this is X, Y, this is 2 variables came up. We have 1 here, 1 here, 1 here. So what will be the function? It will be X or Y bar, right? And this, it can be simplified into X or Y bar. If you distribute X, this or on the end, you will get the same simplified function. Okay, so somebody asked you what is the function, let's say in sum of minterms, sum of product, simplified sum of product. Basically, you need to test all input combinations, or simply you read off the terms from the circuit. This function is either 1 or it is either Y bar. When this function is equal to 1, if X is 1, so we say F equals X and 1, or it equals Y bar and X bar. So that's how we got this expression. Okay. So basically, let me just put this again. This is kind of, it's not an AND gate, but it is an AND condition, let's say. And this is also an AND condition. And this point is basically kind of an OR condition. They call it wired OR. They call it wired OR. It ORs this condition with this condition, but they are not technically AND gates and OR gates, but the conditions implied by these connections is kind of, this is an OR and this is AND conditions. These are AND conditions. All right. So this is all what we need to know about the tri-state buffers for the time being. Any question? Okay. So before we move to chapter 4, let me just, as I usually do, this is a gate that you can buy, that you can use in your system. And if you go to Google, you can find too many integrated circuits, too many ICs that you can buy for this type of gates with different specifications. One of these ICs is 74 LS, let's say 244. 74 LS 244. This is basically an IC or a chip or a block that has 8 of these. As I remember, it has 8 tri-state buffers all together in one package. Okay, you can use them in your system. You may need more than one, you may need one, but they come 8 into one package. So try to search for this number on Google today and read the data sheet, the information about this chip. You cannot, of course, you will not be able to understand everything in the data sheet, but just for the experience, look for this number and you will find it. You will find the corresponding data sheet for this type of gate. So there are other models, but this is one of the examples or the models available in the market. I guess we listed some of these numbers or some of the numbers of the gate numbers before. For example, 74LS08, right? 74LS04. This is inverter. This is inverter. It has six inverters or not gates. This is, I think I remember, look for it. This is, this IC or block has 8 or 4 2-input AND gates. 4 2-input AND gates. 7400, I think, check it, double check my words. It's an AND. This is a NOT. And this is an AND. Double check, and this is a tri-state buffer. So these are real things that you can buy and use to build logic functions. And those who will take the lab, I guess the first 4 or 5 experiments, students work with real components. They design their function, then they bring these components, they wire them up and test and use their functions. One more thing regarding the tri-state buffer, we said that the logic diagram for it is something like this, where we have the enable, we have the, let's say, input, we have the output. Now, this is called active high enable tri-state buffer. What do we mean by active high? Very simple, that this tri-state buffer is enabled when the enable signal is what? Is high. This tri-state buffer is activated or enabled when the enable signal or the enable input is high. Sometimes the enable signal is not active high. It could be something like this, and this is called active low enable, which means the tri-state buffer, is enabled when the input is 0, when the enable input is 0. This is very common. It is actually more common than this configuration. Usually the enable input usually is an active low. What do we mean by an active low? It activates this circuit when its value is low. In other words, 0, when the enable input is 0. This bubble implies an inverter, implies that there is a NOT operation here. So essentially, if you put 0 here, it complements and it becomes 1. But you as a user will only see this. You don't see this. So you need to know that this is an active low. And in order to let you know, usually they put a bar over the E to indicate that this is an active low input. You need to put a 0 to activate this block or this circuit. Now, some other configurations might be something like this. For example, that the output is also complemented. So here it is an active low enable, and basically the output is the complement of the input. So this is basically a tri-state inverter. It's not a tri-state buffer. Tri-state inverter, because we have a value here. When the buffer is enabled, the output is the complement of the input. So you can have different variations. For example, you may have something like this. An active high enable with complemented outputs. The output is the complement of the input when the buffer is enabled. All right. So this is very important. We need to familiarize ourselves with these two terms, active high, active low. We will use them frequently in the coming few chapters. Okay. Any questions? Questions? I think it's clear. We will come back to the tri-state buffers in somewhere in chapter 4 when we talk about a very important logic operation, which is the multiplexing. But this is all what we need to know for the time being. Okay. Let's move now to a very important chapter, which is chapter 4. Chapter 4. And chapter 4 is basically about combinational logic circuits. It is about one type of logic circuits, one type of digital systems, which are combinational logic circuits. In this chapter, we will learn what is meant by combinational logic circuits, and how to analyze combinational logic circuits, and how to design combinational logic circuits. So let's start by very simple introduction. What is meant by a combinational logic circuit? What is a combinational logic circuit? Logic circuit, it implies a digital circuit that is composed of digital logic gates, and or not, nor, or NAND, XOR, XNOR, and all these gates that we know. However, these gates are arranged and connected to each other such that the resulting circuit is called combinational. So what is meant by combinational logic circuit? Basically, we said that any digital system is basically a block, something like this, with a certain number of inputs, let's say x0, x1, x2, or a, b, c, d, whatever variables you may have, up to xm minus 1. Let me put it capital letter, xm minus 1. So these are the inputs. And this system may have, or digital system or logic circuit, may have a certain number of outputs, y0, y1, y2, y3, up to yn minus 1. So we have here the outputs. Now this digital system, which is composed of gates, perform some sort of transformation or mapping from the input to the outputs, such that any output y sub I is basically a function of x0, x1, up to xm minus 1. Of course, for I equals from 0 to, for I equals 0, 1, up to n minus 1. This means that any output is basically a function of the inputs only. It is function of the inputs only. At any instant of time, the output is a function of the input combination. So whatever value you put here, for example, the output will only depend on this input combination. That's why this digital system is called combinational logic circuit. because the output, any of these outputs, regardless of their number, any of these outputs is only a function, is only a transformation of the input combination, input mix, input sequence. So that's what is meant by the combination. So why we are stressing this point? Because in chapter 5, we will see another type of logic circuits, which are called sequential logic circuits. And in such circuits, there are outputs and there are inputs, but the outputs are not only dependent on the input combination, they are also dependent on something else that we will see in chapter 5. So this is very important. Chapter 4 works with such type of circuits that has inputs, outputs, which is something trivial for systems. Any system has inputs and outputs. However, the outputs in such type, in such circuits are only dependent or function on the input combination. That's why they are called combinational. So in this chapter, we will consider only this type of circuits. We will learn how to analyze, which is something straightforward, and we already talked about it. And we will learn how to design such circuits, how to design such circuit to achieve certain functionality or operation. So please keep this picture in your mind, because when we go to chapter 5, we will change it a little bit in order to present a new type, the other type of circuits, which are the sequential logic circuits. So this is basically the definition of a combinational logic circuit. It is a digital system or a logic circuit in which the outputs are only dependent on the current input combination at any instant of time. There is nothing else that can affect the value of the output of this circuit except the change in the input value or the change in the input combination. All right, so let's now go and see how we can analyze combinational logic circuit, which is something we already did. So 4.2, analysis of combinational logic circuits. Analysis of combinational logic circuit. Basically, what is meant by analysis? Given the logic diagram of some combinational logic circuit, we want to find the logic expression or the truth table of the function represented by the circuit or implemented by the circuit. Very straightforward. We have already done this in the last example with the tri-state buffer. So given some circuit or the logic diagram, in the analysis, it is required to determine the logic expression for the function implemented by this logic diagram, or you might be asked to find the truth table of the function implemented by this circuit. So it's very simple. For example, if we give you this we have here, let's say W, X, Y. And here we have Y, X, and this is F. So this is a combinational logic circuit because F of W, X, Y depends only in the input value. It does not depend on anything else. And in this case, what is required is basically to find the truth table of the function represented by this circuit or the logic expression of this function. If we want to find the logic expression, so basically we consider the circuit and we try to find the expression at this point by going from left to right. So at this, and find the sub expressions on the circuit. So the output of this is W and X. The output of this is Y bar. The output of this is WX or Y bar. The output of this is Y bar. So we have here Y bar X or Y bar. And here, what will be the function? The function is basically this NANDed with this. So it will be, F will be WX or Y bar X or Y bar bar. So this is the logic expression of the function implemented using this circuit. What is the form of this function? Is it sum of product? It is a product of sum of min terms, product of max terms. What type of logic expression is this? It is none of the standard forms. It is not a canonical form, right? It is a mix. It is a product complemented. We have here and or, so it's not sum of product or product of sum. But this is the expression that is equivalent or that corresponds to this logic circuit. So this is if we want to find the logic expression. Alternatively, we can find the truth table. We say X, W, X, Y, and we have here F. So truth table can be easily found as we did in the tri-state buffer example by putting all possible combinations, all possible inputs, 0, 1, 1, 0, 0, 0, 1, and the last two combinations 1, 0, 1, 1, 0, 1, 1, 1. So these are the 8 possible combinations. So how to find the truth table? Straightforward. You just plug in the values at the inputs and find out the function f. For example, for the first one, we have here 0, 0, 0 and 0 is 0. We have here 0, so this becomes 1. 0 or 1 is 1. Here we have 0, 0, it's become 1, 0. 1 or 0 is 1. 1 and 1, 1 complement 0. So the first one is 0 and so on. So this is straightforward. We already somehow talked about it in chapter 2 and 3. So the analysis is straightforward. It is much easier than the design, because simply you are given the circuit and you want to analyze it. Excuse me. You want to find the truth table for the function implemented using this circuit or the logic expression that corresponds to the function implemented using this circuit. So please fill in this table at home as a practice or exercise. And there is another example on the slide that is animated, so it's good to look at it for analysis, where you can see how the zeros and ones go through the circuit. So check the example on the slides and complete this table. So this is all what we need to talk about the analysis topic, which is straightforward. Of course, now you may simplify this expression, or you may simplify the function from the truth table if you were asked to. if the question or the problem asks to find the simplified logic expression of the function implemented using this circuit. So it all depends on the requirement or on the question that you have in hand. So this is straightforward. Analysis is straightforward and simple. Let's go to 4.3, which is design of combinational logic circuit, which is the harder part, which is the harder thing. What do we mean by designing a combinational logic circuit? Simply, it is just the opposite of the analysis. In the analysis, we are given the logic diagram, or we are given the circuit itself, and we want to reverse engineer it. We want to find the expression or the truth table that corresponds to the logic diagram. So we have the answer, and we want to find the question. Now, in the design, it is the opposite. We have a description. Usually, we have a description of the logic function that we want to implement. And basically, we want to find its truth table or its logic expression. We only have a description. We don't have the logic circuit. Okay, so given a description for description or specification for some circuit. So we are not given the circuit. We are given the general description of the behavior of the circuit or the operation of the circuit. We want to find the logic expression for its outputs or outputs. The circuit may have more than one output. So this is the opposite of the analysis. In the analysis, we had the circuit and we want to find the logic expression. Here we don't have the circuit. We have a description of the circuit, and we want to find the logic expression of the outputs, and we want to find how the circuit looks. In other words, we want to design the circuit. So usually this is harder than the analysis, because you need to understand the description of the circuit in order to be able to design or implement or derive the logic expression of the outputs. So usually there are simple steps to do that. The first thing is basically to understand the description of the circuit. To understand the description of the circuit in order to determine the number of inputs and outputs. So usually the circuit operation is given verbally. Some statements that tells you how the circuit works, what is the relation between the inputs and the outputs, and you need to design the circuit. So the very first thing that we need to do is to understand the description in order to determine how many inputs are there and how many outputs are there. The second thing is also based on our understanding of the description of the circuit, is to derive the truth table that shows the relation between the input and the output. And the only way to derive the truth table is basically to know the relation between the inputs and the outputs, how the inputs affect the output so that you can fill the truth table. Now, this is a very important step. These are very important steps actually, because once you have the truth table, if I give you the truth table of any circuit, can you give me the logic expression of the function or the functions implemented by this truth table? Yes, we have already doing that in chapter 1 and 3. If I give you the truth table of some function and I ask you about the logic expression of that function, simply you can use the truth table to derive the sum of minterms expression, the sum of minterms expression, the product of max terms. You can take the truth table and simplify using K-map, simplify using Boolean algebra, and so on. So this is very important in the design. Once you have the truth table, you can easily design the circuit. So this is the major challenge that we usually face when we design logic circuits. We need solid understanding of the description of the circuit, of the operation of the circuit to do that. So the next step is the simplify the function using the truth table. We can either simplify as sum of product of sum. Number 4, the last step is basically once we have the logic expression, we can draw and implement the logic circuit. Once we have the logic expression, we can simply draw the circuit and implement it, bring the components and wire them up in order to implement the circuit physically and use it physically. So these are the steps. And as I said, the very important thing in the design is to have a correct truth table that describes the relation between the inputs and the outputs. Once I have this, what is left is straightforward. If you have mastered what we discussed in chapter 2 and 3, then steps 3 and 4 are straightforward because you are now supposed to be professional and expert in simplifying a logic expression given its truth table using algebra or using the K-map. So let's take a few examples. What's the time? It's 10:15. We can take probably 2 examples before we take the quiz. On the design. So it all depends. The design thing, or it all depends on correct understanding of the operation of the circuit, correct understanding and how the circuit is supposed to map the inputs to the outputs. So let's take an example. Design a logic circuit, a combinational logic circuit that has 3 inputs and 1 output one output. The circuit outputs 1 when the inputs has more ones than zeros. So this is kind of a clear description of the circuit because it told us how many inputs and how many outputs and what is the relation between the input and the output. So basically, it explicitly tells us that there are 3 inputs and there is 1 output. So it is given that the number of inputs equals 3. I will call them, let's say, X, Y, and Z. So I call the input variables X, Y, and Z. And the circuit description tells us that the number of outputs is 1, and I will call this output, let's say, F of X, Y, Z. So now it is required to design this circuit that has 3 inputs, X, Y, Z, and has 1 output, F. So this is the first step. From the problem description, from the circuit description, I knew the number of inputs and the number of outputs. What is left is to know what is inside. And in order to know what is inside, we need the truth table. Because if we have the truth table that relates F to these input variables or relates the outputs to these input variables, we can simply know what is the circuit if we know the logic expression. So what is the truth table? What will be the truth table of this circuit? It is given in the problem description. It tells us the output of the circuit is 1 only if the number of 1, if the input has more ones than zeros. So these are the inputs. And the inputs are known either 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, 1, 1, 1. So these are all possible inputs. So what is the output of the circuit if the input is 0, 0, 0? It tells us that the output is 1 if the number of ones is greater than the number of zeros. We don't have any ones here, so the output will be 0. Here we have 2 zeros and a single 1, so the number of ones is less than the number of zeros, so this is 0. Same thing here, it is 0. Here we have 2 ones and 1 0, so this is 1, because the number of ones or the input has more ones than zeros. The number of ones is greater than the number of zeros. And here it is 0 because you have 2 zeros and a single 1. Here we have 2 ones and 0, 1, 1. So this is the truth table. The function is 1 or outputs 1 when the number of ones in the input is greater than the number of zeros, or if the input has more ones than zeros. So this is the second step. This was the first step, determine the number of inputs. The second step, determine the truth table that relates the output with the inputs. The third step is to simplify. Given this truth table, we can simplify it using the K-map. For example, we say this is the 3-variable K-map. Map for F, we have here X, Y, this is Y, and this is Z, right? So this is 0, 0, 0, 1, then 0, 1, 1, 1. So this is very important. You should have practiced using the K-maps because we will use them extensively in chapter 4. We will use them a lot in chapter 4 and chapter 5 actually. So how to simplify? What is F? We can simplify as sum of product. So we look for the ones. We have 3 prime implicants and all of them are essential. This is essential, this is essential, this is essential. So the logic expression will be F. What is F? It is X and Z. or it is X and Y, or it is X bar, or it is Y and Z. This one is Y and Z. So this is the third step. This is a function simplified as sum of product. You may try to simplify it as product of sum by considering the zeros. So you need to take this one, and this one, and then you check for the cost, whether the sum of product expression or the product of sum expression is cheaper. Which one is cheaper? And then use it to implement the circuit. But here the cost will be the same because we have prime implicant, 3 prime implicants. When you take the components, they will have almost the same cost. So try to do this at home. Find the POS expression of the function. It is good practice to do this always, even if the problem asks you to find the sum of product or the product of sum. Always do the two choices, sum of product and product of sum, to practice using the K-map. So this is the third step. Either you simplify as sum of product or product of sum. The fourth step is to implement the circuit, and basically implementing is about drawing the logic diagram and wiring the circuit up. So the circuit as a sum of product, it is X and Z, X and Y, Y and Z, and they are all together to give X. So we have here X and Z, X and Y. Usually we wire them, but for simplicity, I'm writing them like this, Y and Z. So this is what is inside the box. All right, so this is kind of a simple design problem because it already told us the number of inputs, the number of outputs, and the relation between the inputs and the outputs. Okay, the relation between the inputs and the outputs. Okay, any question? Okay, let's take another example. Some time. Design a circuit. Of course, when I say a circuit here, up to this course, I'm talking about a logic circuit, and specifically, I'm talking about so far for about combinational logic circuits, because we only have covered this type of this of logic circuits. So it is essentially a combinational logic circuit. Design a circuit that compares two 2-bit numbers and outputs two values. He called them output 1 and output 0, such that output 1, output 0 equals 0, 0, 0, 1, 1, 0, 1, 1. So the output is 2 bits, It could be 0, 0, 0, 1, 1, 0, 1, 1. And sorry, I forgot to put this. Two 2-bit numbers. Let's call them A and B. So we have 2-bit, two numbers. The first number is called A, the second number is called B. And these two numbers, each of these two numbers is 2 bits, is 2 bits. So what is the output? The output is 0, 0 if A if A equals B and both are even. A greater, if A less than B as a value, then the output is 0, 1. If A greater than B, the output is 0. If A equals B and both are odd, then the outputs O1, O0 is 1, 1. So basically this problem's also kind of straightforward because it tells us the number of inputs, the number of outputs, and the relation between the inputs and the outputs. How do the inputs affect the output? So this is kind of a long problem, by the way. How many inputs do we have? How many inputs? Four inputs, yes, not 2 inputs. We have 2 numbers that are fed to this circuit, A and B, but each of these 2 numbers is 2-bit. So we need 4 inputs, and these 4 inputs, I will call them A1, A0, B1, B0. These 2 bits represent A, these 2 bits represent B, number A and number B. The number of outputs is straightforward because the problem statements told me that the number of outputs is 2, which are output 1 and output 0. So the new thing that we need to be familiar with is this thing, this is the input value, but it is represented as 2 bits. Jumana, could you mute yourself? B is also a 2-bit number, but we are comparing this value with this value, which is represented, each of which is represented using 2 bits. And the relation between these inputs and the outputs is basically given in this equation. If A is greater than B, if A is less than B, and so on for different cases. Okay, so in order to do this, we need to build a truth table, and the truth table will be kind of big. What is the size of the truth table in this case?
16.
Yes, we have 4 inputs. So we'll have 2 to the power 4, so which is 16 input combinations, 16 rows, 16 rows. So I have to erase what I have on the board to draw the truth table. So the truth table will be, we have A1, A0, B1, B0, and we have output 1 and output 0. So 0, 0, 0, 0. Remember that these 2 inputs represent A, and these 2 inputs represent B. And this is the output. So now we have 0, 0, 0, 0, 0, 0, 1. We have 0, 1, sorry, 0, 1, 0, 1, 1. 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, sorry, 0, 1, 1, 0, 0 1 1 1. So usually you need to list all the combinations, but keeping in mind that these 2 bits represent A and these 2 bits represent B. We have 1 1 to make sure it will fit. I'm just filling the table. So these are all the possible combinations. And all what we need to do is to keep in mind the equation that we have on the previous, let's say, previously. So here we compare. This is A and this is B. What is the relation between A and B? They are equal and they are even because they are zeros. So the output will be, if you go back to the equation, will be 0, 0. Here we compare A with B. And A is less than B. And if A is less than B, the output should be 0, 1. A is 0, B is 1, 0. In decimal, A is 0, B is 2. Still is A is less than B, so it is 0, 1. 0, 0, 1, 1. So still is A is less than B, so it is 0, 1. Here, 0, 1. So A is 1, B is 0. So A is greater than B, so the output should be 1, 0. Both are equal. They are equal and both are odd. So the output should be 1, 1. So when you do the comparison, you check the relation. You can find the value of the output by checking the equation that we had. Here, A is less than B, so it is 0, 1. A is less than B, 0, 1. A is greater than B, 1, 0. A is greater than B, 1, 0. Equal, here, both are equal. They are equal and both are even, so the output is 0, 0. A is 2, B is 3. So A is less than B, so it is 0, 1. A is greater than B. A is greater than B. A is greater than B, so it is 1, 0, 1, 0, 1, 0. A equals B, and both are odd, so the output is 1, 1. The output is 1, 1. So basically, we have the truth table, and now we need to keep in mind that we have 2 outputs. So we need to simplify 2 functions. Yes.
دكتور رقم نمبر 5 ورقم 10 9 يمكن في واحدة 11 وواحدة 00 ليه يا دكتور؟
رقم هذه
5 11 وعندك اللي هي العشرة 10 طلعناها حطيناها 00 الاوتبوت ليه دكتور؟ لانه اثنتين متشابهات.
هلا هاي 01 01 ماشي؟
بالضبط متساويات.
This is A and this is B. Both they are equal and both are odd. إذا برجع على الإيكويشن اللي كتبتها قبل شوي لما يكونوا متساويات وأود الاوتبوت لازم يكون 1 1. هلا العشرة هاي هالعشرة مزبوط هم متساويات مزبوط
صحيح.
بس التو فاليوز ايفن يعني هذه كم بالديسيمال.
ايوه تمام.
هاي اثنين. فاذا برجع على الايكويشن لما يكونوا ايكوال وايفن لازم احط 0 0 الاوتبوت بيكون 0 0. تمام. So the first step was knowing the number of inputs and the number of output. كان في محمد بيسأل I think محمد بيسأل عن عدد الانبوتس. سارة انت بتجاوبي فيه يعني؟ محمد بيسأل عن كيف عرفت عدد الانبوتس. زي ما حكينا هو حكى لي انه السيركت it compares two values A and B and each of these values is 2 bits. فاذا عندي 2 values كل واحده منهم على شكل 2 bits ممثله باستخدام 2 bits، فبالتالي عدد الانبوت لازم يكونوا 4. تمام محمد؟ اوكي. طيب هلا straight forward، طالما معي التروث تيبل as long as I have the truth table deriving the logic expression is straightforward. If I am familiar with the K-map or the Boolean algebra, I can easily find the logic expression. So let me do one of these outputs and leave the other one for you to do. So if I take output 1, output 1 now is a function of 4 variables, which are A1, A0, the order is important, B1 and B0. So now we need to fill the map. This is output 1, so I'm taking this column. So it is 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1. So this is the K-map. This is the K-map. And what are the prime implicants? We have 3 prime implicants. We have this one. We have this one. Right? And we have this one. And all of them are essential. So what will be output 1 as a function of A1, A0, B1, B0. So the output is a function of these 4 variables. So it will be this one. What is the expression for this one? It is A1 ANDed with B1. So it is A1 ANDed with B1. Or this one is A0 ANDed with B1. Or it is this one, which is A1, A0. Okay? Leave some space if you are writing with me. Leave some space and find output 0. Output 0, if you do it, will be B1, B0, or A1 bar B1, or A1 bar B0. So you need to fill the map for output 0 and do the simplification. You will end up with this. And the last step, draw the logic diagram for output 1 and the logic diagram for output 0. Okay? So this is all what we need to know. Step is basically to find the number of inputs, the number of outputs, and the truth table. Once you have that, the design is straight forward. Okay? Any questions? Let's now try to do the quiz.